How do we get the state space formulation? Remember when we have the car problem, let's say this is the traction, and then the velocity of the car is going that way. We developed the Newton's law for this car, like this, yeah. Let's say there is no friction, there is no disturbance, so we have the traction is equal to max double dot, and then I can express 1/m times t, yeah. So to create state space formulation from here, I create the two states. Okay, one of the state is the displacement, and the other state will be the velocity. Okay, so what I can say here, if I put x1 dot, that will be the same as x dot, yeah, and x dot is simply x2. And then what about my x2? X2 dot, yeah, why is that so? Because I add dot in here and add another dot here, this become two dots, okay, and this one simply 1/m times t. Okay, so I can create my state space equation here. X1 dot, x2 dot, simply what, x2, right? Like this. Okay, so this is already in state space form, yeah. And then I can also say here that my y, or the output, to be matrix C multiplied by x1 and x2. Okay. So the y in here is the output, the same kind of output that you also see in transfer function. Yeah, basically the output of the state space is the state that you are interested in. Okay, what if my output is the displacement? How should I write down the C in here? If my output is equal to x1, then what is the matrix C here? Yeah, 1, 0, yeah, 1, 0, like this, and this is x1, x2. So 1 times x1, 0 times x2, that will be x1. Okay, what if I want the output to be displacement and velocity, two of them? What will be the C? Huh? 1, 1. I want y to be x1 and x2, like this. What's the C? Huh? Sorry? 0, 1, 0, 0. Like this? 0 times x1, 1 times x2, I get x2. 0, x1. No lah.
Yeah, 1, 0. 1, 0, 0. 1, 0, 0. Identity.
It's identity, okay. Yeah, it has to be identity, okay. Right. So when we write down a state space equation, we normally write it like this. Okay. So the x in here is generally a vector, not a scalar. Yeah. Let's discuss about stability. Yeah. Do you remember the bistability in the transfer function? What's the definition? The pole is at open left half plane. Open left half plane. Okay. So what is the result of that? What is the effect? That's the condition, right? The pole on the open left half plane is the condition. So what is the result of that condition? No. If you give it a constant input to it, then the output will be also a constant. Okay, so you give it a bounded input, the output will be also bounded. If you give it temporary input, the output will be let's say you give it an impulse that is temporary, right? The output will be 0. Okay, so if you disturb it a bit, if the system is stable, it eventually will go to 0. Okay, is that clear? That is for the Bible stability. Yeah. Now for stability for state space, there are three cases lah, I will say. The first one is Lyapunov stable. The second one is asymptotic stability. And the last one is unstable. Okay, for this one, Lyapunov stable, the eigenvalue of A will be, one of them is 0, and the remaining are on the open left half plane. So in this case, eigenvalue is on the left half plane. Okay, on the left half plane, and the 0 eigenvalue has Jordan block of order 1. Okay, this is Lyapunov stability. For this case, what's the eigenvalue of this? 0. It has two eigenvalues. One is 0, and the other one is 0 also. Both of them are 0. Okay, upper triangular matrix. Eigenvalues are the diagonals. But this one is in Jordan form. Jordan form order 2. Okay, so the eigenvalue is located on the left half plane. Yeah, not open. Yeah, so 0 is also included. Okay, however, it has Jordan block of order 1. This is the Jordan block. So this is not Lyapunov stable. This is unstable. Okay. For asymptotic stability, eigenvalue of A is located on the open left half plane. Yeah, this is the counterpart of Bibo stability. Okay, unstable. Okay, eigenvalue of A is on the right half plane. Okay, open right half plane, and this case, yeah. For this case, it is unstable.
Okay, and open right half plane, and your eigenvalue has
Jordan block of order 2 and greater. Okay. What about the case of, let's say I have A matrix to be like this? What's the stability type of this? It's Lyapunov stability. Yeah, Lyapunov stable. It doesn't have Jordan block. What about this one? This is Lyapunov also. Yeah, Lyapunov, because -1 is here, right? And 0 eigenvalue order 1. There is no Jordan block for the 2 or greater. Okay. So what is the effect if the system is asymptotically stable like this? For a system like that, yeah, You see, when your system is like this, yeah, if it is asymptotically stable, then for all initial conditions, any kind of initial condition, yeah, limit t go to infinity of x t will be 0. So all of the states will go to 0. Okay, you disturb it a bit, then all of them will go to 0. And that is asymptotically stable. Now I will give a case of this when A is 0, 1, 0, 0. Yeah, this is unstable, yeah. And our B is like that, 0, let's say 0, 1. So 1 over m, I replace it with 1. How to make this system to be stable with an input U? U is the control input. How do we make this system to be stable? Any idea? I cannot change the A. B also cannot change. What's the U we need to use here? What's the U? So we will use U to be minus K times X. K is our feedback matrix. X is the state. Okay. So the system becomes minus B KX. And so this is A minus BK times X. You see, this is the closed loop system. Yeah, this is still in open loop. After we add input to be minus KX, it becomes like this. So to stabilize the system using the feedback control input, we have to make A minus BK to be stable. Yeah, so we want eigenvalue of A minus BK to be on open left half plane, and there is no Jordan block. Jordan block is this one. Which order? Oh, the order. This is second order, like this. This is first order. Jordan block means you have repeated eigenvalues. Yeah, it has repeated eigenvalues, and then on the corner of your diagonals, you have an item in there. This one, like this. Yeah, it becomes a Jordan block of order 2. If it is order 3, this is order 2, yeah. If it is order 3, then you have 3 repeated eigenvalues, and then there is another term in there, like this, for example. This is all 0, yeah. So you have 1 in here, 1, 1, like this. This is the third order. Okay. So the problem in the state space control is that usually we are asked to design the K in here, yeah, to stabilize the system. And any kind of, not any kind, yeah, most of cases of regulation, control, or let's say you want to regulate the speed of the car, yeah, you can transform it into stability problem like this. So you have to design a matrix K to stabilize the system. But the problem is that not for all B, sorry, not for any A and B there exists a K. Okay, so not just for any kind of A and B, that there exists a K to stabilize this. Okay, and so there is a concept of controllability that you have to know, yeah. controllability, and also we have stabilizability. Yeah. If the system is controllable, then there exists a matrix K for which you can stabilize the system and also to adjust the eigenvalue location. You can place it anywhere you want. But not all systems are controllable. Yeah, fortunately for this system, this is controllable. This one controllable, although this is unstable but controllable, so you can find a system feedback matrix to stabilize the system. Okay, so controllability I will discuss at some other time. However, I want to let you know that this will be the discussion for the state space. What time is it? 15. Yeah, okay. So we end the class here. We see you again on Wednesday.